This is a very, very long-term process, millions and millions of years, okay? So the fact that the ocean is alkaline and sort of its center point, where it sits in acid-base space, is set over very, very long time scales. But if you were to look at a pH measurement, this is a very idealized version of the pH measurement profile in the ocean. You see that the surface waters are a little on the plus side of 8, about 8.2. You go down here to the bottom of the euphotic zone, and waters become a little more acidic. Down here in the middle depths and the deeper depths, there are changes that are associated with the ages of the deep waters that are circulating throughout the ocean, okay? And these changes are in the neighborhood of 0.6, 0.5 pH units or so. And those are purely natural, okay? And they happen through reactions involving carbon dioxide and the associated bases. Right? So carbon dioxide gas from the atmosphere can dissolve in water, or carbon dioxide gas dissolved in water can move into the atmosphere. Series of equilibrium reactions that all involve hydrogen ion and these basic forms of carbonate. And you're going to be tested on this. All I wanted to say here is that these are natural reactions. Photosynthesis, which consumes CO2, water and nutrients, and makes organic matter and produces oxygen, changes the pH of the water around it because it consumes CO2. The reverse of that, respiration, changes the pH of the water because it releases CO2, okay? Carbonate mineral formation and dissolution also have acid-base reactivity and change the pH and the carbonate character of seawater chemistry. Okay, that's the end of part one. Hopefully, I put that right up front so that if you're going to fall asleep, that was just going to get you going. So here's where we are so far. Ocean chemistry is slightly basic, and this is set by very, very long time scale processes. There's natural variation in pH and carbonate chemistry, and these are controlled by the internal carbon cycles in the ocean, change the distribution of these carbonate minerals, carbon dioxide, carbonate ion, bicarbonate ion, okay? So there we are. Okay, so now, ocean acidification. I need to give you some background on this because it just really is terrifying, right? Ocean acidification, right? And so what exactly is that? Well, you have the ocean, and you pour some acid in, and then you go running in, and then when you come out, you turn into the Joker. and that's not it. Okay. But now you see why we have to give a scary, punchy name to it, because what ocean acidification is, as it truly is defined in its usage now, is the changes in carbonate chemistry, not just pH, and the acid-base balances in the ocean. They result from invasion of anthropogenic CO2 in the atmosphere. Right? There's always been CO2 in the atmosphere. The CO2 is higher now, and so the CO that's going into the ocean is changing the pH. And this is a pretty narrow definition that's included within all sorts of other things that are fairly complicated. And this really is getting kind of squishy, right? And so I need to give you a little background here about what we're certain of and why it is that we actually need to pay attention to this. Okay. Now the first thing that we know is that atmospheric carbon dioxide is now higher than it's been at any point in the last million years, and probably longer, but about 1 million years is as long as we have data. These blue dots here, you're probably familiar with this. This is the Keeling curve that were a set of measurements taken at the top of Mauna Loa by Charles Keeling, the late Charles Keeling from Scripps Institution of Oceanography, which was a completely bootleg project. He was denied funding, I'm told, for many years after he started the project. And these were the first high-quality CO2 measurements in the atmosphere. People didn't know how to make these measurements well enough to really resolve this level of detail here. What I'm showing here is the mixing ratio, and you might hear me go back and forth between these units of parts per million and microatmospheres. So they're the same numerically. And once this started to be believed, and it was shown obviously that this was rising, that the composition of these CO2 was coming from fossil fuels, that the amount of CO2 that was going into the atmosphere was of comparable magnitude to the amount that was being released anthropogenically. People got more serious about this and started to do things like looking into ice cores. So when ice accumulates, it traps gases in the matrix, and you can then drill down into the ice core and chop it up and extract the atmospheric gas out of that and measure its content. And here is from a place where the ice is really accumulating quickly. And so you can get high resolution atmospheric carbon dioxide concentration information. And this goes back to, you know, the dawning of the United States of America. And what you see is that these historical data were about 280 parts per million and then rose and merged almost exactly with the Keeling record, which then started to really accelerate. And this is sort of, you know, industrial revolution timescale. So things were low and maybe creeping up, and then the industrial revolution hit and things really started to accelerate. Okay, so now I said million years. Now here's some longer ice core data from a paper that came out in Nature. I think I remember the author, Luthi or somebody like that. But these are ice core data, and this is a temperature proxy here that's based on the isotopic content of the water and ice. And all you need to know is that lower numbers here are cold and higher numbers here are warm. And so who knows what this up-down cycling is over the last million years? Somebody. Everybody thinks this is such an easy question that they don't want to answer it. But
Milankovitch cycle?
Well, maybe. I mean, more directly, it's the ice ages. Right? Now, we're still not certain that Milankovitch cycling is what was driving the ice age intervals, but there is some suggestion of that. And essentially, you know, these are ice ages, and these are interglacials. So this is warm, this is the glaciated earth. And right along with this is the carbon dioxide record in these same ice cores, okay? And what you see is that they've got very much the same character, enforcing in time. And during all of the ice ages, we have very low carbon dioxide in the atmosphere, maybe 180 parts per million. And during all of the interglacials, we had higher carbon dioxide in the atmosphere, but never any higher than about 280. Okay? Then if you were to put this plot here, that's what it would look like. Okay? So it's not only a bigger change, but it's much more rapid than anything that we think we've experienced in the last million years or so. Okay. Now people, you know, this is why I have to say this. There are people that will argue those points, and they're not arguable. Those are just facts. That's absolute certainty. The second thing is that if you put more carbon dioxide in the atmosphere, more carbon dioxide goes in the ocean. Now, we used to think this is a good thing because we thought, oh, the oceans are you know, delaying climate change and are reducing the rate of CO2 accumulation in the atmosphere, because just thermodynamically, the amount of CO2 that's dissolved in water is related to the partial pressure in microatmospheres. That's carbon dioxide in the atmosphere times the thermodynamic constant. Okay? And, you know, of course, we weren't thinking, oh, we need to be measuring CO2 content in the ocean from 1750 onward, and so there aren't very many places where we really got good data. But off of Hawaii, there's a time series station that's been in place since the late 80s, early 90s, and they were making these measurements. And here's the Mauna Loa atmospheric curve, and it's rising right along like this. And here's the Hawaiian Ocean Time Series CO2 curve. And there's a lot of variability here, but the trend is following the atmosphere right along with it. Okay? So carbon dioxide in the atmosphere goes up, carbon dioxide in the ocean goes up along with it.